we are going to expand on the lecture from Calc1, which is just area below the curve. So now, instead of working on a problem that might look like this, which is Calc1, you have some kind of a function, f of x, and then you would like to know what is the area between x equals a and x equals b. We set that integral in Calc1 as a definite integral, looking at the area between a and b, which are both x values, so you can also think of them as x1, x2. So integrating the function f of x dx. And I can't emphasize enough the multiplication symbol in between f of x and dx, because dx is the width of infinitely thin rectangles, and f of x, when we compute it at the various points, is going to be the height of those rectangles. So height times the width is the area of the rectangle, and then you have infinitely many of those rectangles added so that they fill all of the space under the curve. And that's the reason why these integrals would compute area under the curve. Integrals are accumulations. So because that integral sign is actually stretched s, letter s, that it's stretched to make up a new mathematical symbol, and s stands for the sum. So we are adding infinitely many of these rectangles, and thus we are getting the entire area under the curve. You might want to get into a use of drawing the representative delta x rectangle. And we also know that delta x is the same as dx from calculus 1. So this representative rectangle is going to save our skins over and over and over again as the course goes on, because we will have to set up integrals. So now that we have some of this knowledge from calculus 1, I'm just going to do a single example, maybe prove the formula for, let's prove the formula for, let's say, area of a triangle. Let's prove that formula using calculus 1. And then we are going to upgrade this calculus 1 formula into now our section 6.2 area between two curves. So let's go first and do an example from calculus 1. I'm going to simply draw a triangle here on a xy plane. I am going to call, this is obviously origin, it's 0. That's our A. It goes, oh sorry, let's put B over here on top, B. And value on the bottom, let's call it A. So now, to set up the area, I would need to know what is the f of x. Now we see that's a straight line. The line that falls to the right must be negative. The slope is rise over run, which is b over a in this case, times x. And then we have plus b because that is our y-intercept. So now, what I'm going to do is, I have the function. I'm going to set up my area as integral from 0 to a of the function, which is negative b over a x plus b, times dx. So now all we need to do is to integrate. It's a linear term, so negative b over a times x squared over 2 plus bx computed from 0 to a. The definite integral is computed by plugging in the upper limit first, in our case a, and then minus the lower limit, which is a 0. Now 0 is going to kill everything, so we don't have to plug that one in. We have negative b over a times a squared over 2 plus ba minus 0 if you plug the lower limit. And what do you have? When you plug in 0 into x squared and you plug 0 into bx. So first 0 is for the first term, second for the second term, because there are two terms there. Right? So one of these a's will cancel, and when a cancels, what do you get? Anyone? Negative BA over 2 plus BA. Awesome. So now we're going to figure out the common denominator here. Are we all good with this? Observe there's no plus C because it was a definite integral. We had limits, so no plus C. And we have 2AB minus AB is just AB over 2. Now we know that this area, the A is the base, and the B is the height. And you, at some point in life, had to memorize the formula as BH over 2, right? 1/2 base times height. And you see it right there. So this is how awesome calculus is. You can literally forget all of the area formulas and volume formulas that you learned before, because you can now derive them all by simply drawing the shape and just integrating whatever you have. So this goes for all of the formulas that you know. And as we go along, we are going to deal with the circle, and then if you make it to Calc 3 because you want to or have to, you will deal with the volumes and other things, and we'll be able to show also volume of the sphere and everything else. So that's a little preview of what you guys know from Calc 1. So now going to Calculus 2, I'm going to introduce two functions. Between a and b. This is going to be my f of x. This is going to be my g of x. And I would like to know what is the area right here. What is this area? So now, what can I do? Well, if you carefully observe, if you completely ignore g of x, so I'm going to erase it for a second, and then I'll bring it back. So if you're ignoring g of x, you see that by setting up the integral for f of x, you can find the area of the green plus all of the white underneath it, right? So if I go and calculate area of f, I'm going to have integral a to b of f of x dx. And that is going to compute all of this stuff here, all of it. So it's going to compute what we need and some extra stuff. But then hopefully you also see that if you compute the area of G, you are only going to get this part here. Do we see that? Because that's the area below G. So that one, A to B, is going to be G of x dx. So now the area that we actually need is a simple difference between these two. The f of x contains the green and the white, and the g of x contains only the white. So if you subtract them, you will be left with green. So area is going to be AF minus AG, which is our integral a to b of f of x dx minus the integral a to b g of x dx. And that, now from calculus 1, you have the theorem that says that we can put this into a single integral from a to b, and here are the parentheses, f of x minus g of x dx. This formula is your first formula for Calc2 that you are remembering, and this formula is the formula that computes the area between two curves. Now we're going to also write the formula for y direction immediately. So area is equal to, we use C and D, of f of y minus g of y dy. And I will explain the difference shortly. So here's your area between two curves. So when everything is in terms of dx, you will be looking for the area, f of x is the top function and g of x is the bottom. One of them always has to be on top, the other one will be on the bottom. And if you're looking sideways as the dy, it's right minus left, which means f of y is the one on the right, g of y is one on the left, so it's going to be f minus g. Now I will do examples so that will be clearer as we go on. So first introductory example here, let's go with something that it's obvious. I'm going to actually draw a picture and then I'm going to put functions there and then we'll cheat off of that. So say, I'm going to put that actually in the middle. Say we have a parabola that opens downwards, goes up to 4. It's going to fall like this. I'm just going to do a little better job in parabola. There we go. So we have a parabola that opens downwards from 4. And then I might want to set up a linear line that goes through these points like right there. And I would like to know area between these two curves. Now this is number 1 and this is negative 2. Those are given to us so we can actually figure stuff out. So what is area between two curves here? Again, I'm going to color it. So the first piece of a puzzle is that you are trying to figure out whether you are supposed to use dx or dy. Because if you are supposed to use dx, you're using the top formula. If you're using dy, you're using the bottom formula. Now, what's the difference? Well, dx piece looks like this. And dy piece looks like this. If you guys remember your Calc 1, those are the representative rectangles. And now you have to use them because you can't set up the integrals without them. So now let me try using dx first, see if it fits. So I draw dx rectangle. And what I'm looking for is that the ends of this rectangle always write the same function as we swipe from left to right. And in this case, that is true. So we get to keep using dx in this problem. So if you look at dx, the top of dx rectangle will always ride along x square graph around the parabola. And the bottom will always ride the linear line. If you are to draw a horizontal one, You see that that's not a case. Because in this position, the left and the right side of the dy will be touching the same function. And you can't set up the integral there. Because why? Not a function, right? Remember the vertical and horizontal line test.
Is this also related to working the parabola?
Yes, it is related to that, but when we get the parabola going sideways, we'll be using dy.
Right, that's what I'm saying. It's related.
Yes, it is.
It's related. Formulas users are related in the same way as Calc2.
Yes, we are. Yes, because we are upgrading those concepts now. Very good. So guys, just by drawing this rectangle in, I know that the top function f of x is the parabola, the bottom function is the linear one. Well, let's first discover them. So f of x is the one on top. It's clearly negative x squared plus 4. Negative x squared because it opens downwards, and plus 4 because it's shifted 4 units up. And the linear line, well, g of x, we have a positive slope because it rises to the right. And the slope is 1 over 2, 1/2. So 1/2 x plus 1 because it goes through y-intercept 1. Remember, it's mx plus b. B is the y-intercept. It goes through 1, 1's y-intercept. The slope is 1 unit up, 2 units sideways. So rise over run, and it's positive. We rise 1, go 2 units. If you want to look at this way, rise 1, go 2 units to the right. Awesome. So I have my f and g, and it's very easy now to set up the area because the representative rectangle tells us the top minus the bottom, which is negative x squared plus 4 minus 1/2 x plus 1. I'm going to put now these guys dx because we need to put all of it because it's time dx. It's times dx. One crucial problem here. What are the limits of integration? What are the a and b? And how do we find them? Yes. Please. Very good. Intersection of two. Now, how do I solve it? How do I use the concept of intersection to find the a and b? Set what them equal to each other? Very good. So functions f of x and g of x intersect at those 2 points. They have the same y value and the same x value at those 2 points where x values are your a and b. Since you have 2 intersection points, the one on the left is going to be a, its x value is a, and the x value on the right point is b for your limits. So, to find limits of integration, set f of x equal to g of x and solve. Now we are probably going to get some horrend numbers now because I just put these functions. And we solve this. So move everything to the same side, maybe even multiply through by 2 so we don't have fractions. And now solve this using any witchcraft you know. Whatever. It's not a pre-calculus course or algebra course, wherever you learn this. So your job is to find 2x's, whether it's going to be factoring if you remember it, whether it's going to be completing the square if you remember it, which is quadratic formula with the negative b plus minus square root and the rest. Whatever works. Just do it to get those x's out. Yes. I moved both of these to the right. So, and then I moved 0 again. So I moved negative x squared, become positive x squared, 1/2 x stays positive, and then -4 becomes -3. And then I just moved 0 on the other side. Cool. So now that I have this, I'm going to use -1 plus minus square root of 1 squared minus 4ac, so plus 4, 24, 48. What? What are the chances of this? Should have bought a ticket. You know what the odds of this are, actually? It's like you put whatever two functions in and this happens. 1 plus 48 is 49. If those of you are not getting what's happening right now, square root of 49 is 7. Okay, so we're getting the actual whole numbers to work with. Actually, we're going to have fractions, but still. We're not getting a decimal value of, 1.37893354. We're getting actually 7. So, actually, you know what? Class is over because I have to make it and buy a ticket in time. This is going to give us two values, and those two values will be your a and b for limits of integration. Obviously, lower number is a, and the higher number is b. So 7 minus 1, also negative, both negative, so -8, -2, and 6 over 4, 3/2. So these are our values. -2 is the lower limit because it's a smaller number. So now our area integral is -2 to 3/2, and then we just use some algebra to put this stuff together. So -x squared minus 1/2 x, 4 minus 1 is +3. All of that in parentheses, and then dx. So now when we integrate, we get -x cubed over 3 minus 1/2 x squared over 2 plus 3x from -2 to 3/2. Plug in 3/2. So we have 3/2. That's 3 3's, but there's 1 in the denominator, so 1 will cancel. So you have 9 8's there. Plus minus 9 16ths plus 9 halves. So you have 3 minus signs now, so that's still a minus. And you have 2, so that's 8/3. And then you have that minus dies because of the square, so you have a -1. And the negative in front is +1. -6, +6. Just keep counting these negative signs. They're all over the place. Try to see if you collected enough of them. Yes?
Why did you make it negative at the beginning? The integral? You had the whole function negative?
Which whole function? Can you?
When you put the combined one, the -x squared minus...
Oh, because I'm solving from here. It's -x squared. See, on the bottom, I get to manipulate this any way I want. Because if the equation has equal sign here, I can move terms to the left or to the right. It doesn't matter which way I move them. And I end up with these. Right. Over here, you're stuck to work with what you have because there's no equal sign to move stuff to the other side. Okay. And you can't really multiply through by -1 because they are only allowed to do that in equations, right? This is an expression solving forward, so there's no moving things left and right. So I'm stuck with it. Okay. I'm stuck with the negative here, I'm stuck with the negative distribution there, and I have to use them. All right, so now that that's clear, we're going to do some of the calculations here. Now we're observing, guys, that all of these common denominators over here are working on 16, and then we have 8/3. Awesome, right? So everything is 16, so that's going to be common denominator over here on 16, and then we're going to keep this one 8/3 for one more step, and then plus 7 over here. So 16, so that one stays as is. 16, so that's half is 8 plus, so I hope that's like 72 or so. And then 8 is a half, negative 18. There we go. Negative 27 plus 72 over 16 minus, and now thirds 21, so minus 8/3 plus 21 over 3 to get those two together. Okay, so now what are we doing with 27 and 72? Calculator? Nah, we're not going to do calculator, right? So 44, 45 is good enough? 26? All right, let's go with 26. It's like, how many calculators are going to give you? Oh, wait, one, it comes from, right?
User error, 45.
Oh, user error. Okay, now I get it. All right. So, guys, 72 minus 27 without the calculator. This is like a long lost art. What I'm going to do here is I'm going to add 3 to both of these numbers, because I want to make the one on the bottom to be 30. And then this one is 75, and now it's clear it's 45. Huh. So we have a 45 over 16. I know it's magic, right? And then 21 minus 18, we can do minus 8. We can use the same trick. Or we might also just put 13 over 3. Now what? So this is just like the most difficult thing in Calc2. You're good with the rest. It's like punching these numbers correctly in the calculator will probably be the worst nightmare out of everything you do in this class. So I'm going and calculating this by hand. And what are we going to do for 16 and 3? The what? Yeah, what is the common denominator? 48. So now 45 times 3? Yeah, 135. How do we know that? Because 40 times 3 is 120 and then 15, right? Plus, what are we going to do for 16 times 13? You could. But how much is 16 times 10? 160. And then 3 times 16 is 48, so 208, right? Awesome. So you say you can't do this. You can. So what do we get? 343 over 48, since nothing, right? Can't reduce because we didn't go. Awesome. Spent more time on computing this than actual calculus.
I thought it was a minus.
No, it's plus, because it's 21 minus 8 is positive value. You have minus 8 and then plus 21. 21 is bigger than negative 8. So 21 minus 8 is positive 13, and then addition. So now we're going to take like a 15 minutes break for you to kind of catch up with calculations, and then we're going to go do more calculus, right, in 2 minutes. All right. I'm going to make sure that stream is going. Yep. All right, good. All right. Ready for the next example? All right. Example 2. Let's find the area between y equals, what are your favorite functions? Like trig functions your favorite? Awesome. So let's go with 2 sine x and a cosine x. The first two intersections that you can find when you graph this. Maybe we can keep it in positive. I don't know. Let's see how. Would anyone like to go to the board and just graph this? This is about the time where I just hear crickets and everything. But you can use this grid actually, and I'll give you my trusty marker. It's technically almost like him doing this is like cheating. I got it myself. Yeah, whatever we get to the right. Sine x. Yeah. So sine x is going to be twice as tall, and then the cosine is going to start its original, fold, halfway, and go up. Awesome. Yay! This is how you graph trig functions. Awesome. So the 2 in front of sine x, is going to multiply the amplitude of sine by 2, which means that the sine is going to be twice as tall. Cosine is just default, so starts at 1, falls into -1, and rises back up at y equals 1. And what we want to find here is the area between these two guys. So let's pick this area here. I will redo this obviously on tablet, but pick this area and do it. You know which one is on top, which one is on the bottom. You will set two equations equal to each other, try to find the intersections. Let's see how it works. So what are we going to do for limits?
Cry?
That's what I heard. There's no formula sheet that helps there. Just got no stuff. There's no way, yeah. Absolutely not. Yes?
I'm thinking I don't want to actually add cosine to both sides to get two sine.
Well, we set them equal to each other first, right?
Yeah. And
Okay.
Then you divide cosine from both sides to get two tangents.
What happened?
Like if you add cosine to both sides,
Mm-hmm.
like divide that cosine to both sides. If you do like the cosine from that,
Okay, so divide cosine into both sides, sure.
so you're gonna get two tangent equals 2 of 1.
2 tangent x equals 1. Move 2 over. And there it is, right? Yeah, so this is where the in-depth knowledge of Precalc2 gets really handy. Now, this is not landing on any of the known values, right? You would actually have to apply arctangent to both sides, and you will have inverse tangent of 0.5. That's not going to be any of the values that you are used to, like, you know, square root of 3 and square root of 3 over 3 or 1 or anything like that. It's not arbitrary, it's exact point, but it's not one of the values you're used to. The second part is, where is the second point? Right? When does that happen? Yes. One period away. Awesome. And what's the period for tangent? Pi. Good. So whatever we get, it will be plus pi, which is plus 3.14 in other words. So, and maybe you can see, just maybe you can see that this one over here and this one over here, they're the intersections that are pretty much right there. They're pi apart. So this is where your A is, and this is where your B is. So to find A, it's going to be x equals inverse tangent of 1/2. Now you will set your calculator to radians and find that decimal point. 1 decimal, 2 decimals is fine enough. So make sure your calculator is in radians. So I'm getting that A is 0.46, which means that B has to be 3.6. Was 3 by pi, 3.14.
I get how you got down to the fact that it's tangent. How did the different point was inverse tangent?
You need to solve for x. And to get x alone, you apply inverse tangent on both sides, and then they cancel because it's the inverse function. So here are my wonderful limits of 0.46 and 3.6. We integrate these and then use these values. Again, we're computing as radians, so sine of 3.6 is just fine. Yes.
Where did the two numbers for A and B come on?
The A is just a calculation, and then b is a period, happens period later,
Oh, okay.
which is plus 3.14 pi.
Because the pi is the
Period for tangent, yes. So now integral for sine, we get negative 2 cosine x minus sine x computed from 0.46 to 3.6, and all of this equals a number, and it's great. So that's the part. Again, one more time, I can draw the representative rectangle delta x, and you see that the top is touching the top function, which is 2 sine x, the bottom is always touching the cosine x, and they go through.
So why is the bottom one negative?
What do you mean bottom one negative?
I mean, it's not like negative when you switch stuff around.
Which one are you talking about?
The integral up top. It's 2 sine x minus cosine x.
Yes.
Then why is it 2 cosine x minus sine x?
But integral of sine is negative cosine, and integral of cosine is positive sine, and I just copy the minus.
Right.
All good. All good? Oh, it was a scratch. Let's take a look at another example. I'm going to quickly jump and show in the textbook homework. So what are the types of problems that you might want to consider? We have, and I will be drawing this directly on the page. So pay attention. Let's take a look at problem 7. This is page 417 for those of you who want to follow in the textbook. So if you're looking at the problem 7, you see that you have the exponential function, you have a linear function, and I would say clearly dx is the one that needs to be there, because dx stretches vertically, and the top is always touching the linear function, the bottom is always touching exponential, so it's linear minus exponential. You integrate, figure out the limits. The same goes for problem 8. You have a secant squared function, you have a cosine squared function. Cosine is on top, secant is on the bottom. When you subtract them, right, it has to go top minus bottom. Again, intersect two functions, make sure they add up. One to the side. We're looking at problems 23, 24, 25 now. If you look carefully at those problems, delta x will not work. Because as you start sliding delta x from left to the right, the function on top is going to change when you get to 0. And that's not good. Because delta x has to swipe in one sweep from A to B. And it never, ever, ever can leave a function that it was following. If you start following the square root of x squared, x over 2 plus 1, it has to go from A all the way to B, following that function on the top. But it switches. So that's not good. However, if I switch to dy, which is horizontal rectangle, you see that as it swipes from 0 to whatever this point is, the right side always touches the red and the left one always touches the right. The left one always touches the black function. So look, if it's here, again, this edge touching, this one, there. So you see, no matter where you draw, horizontal representative rectangle, this is the one that tells you which formula to use, dx or dy. So clearly we are going to do here now red minus the black. Red minus black, right minus left for dy's. It's always right minus left for dy's. So I need you to guys to look at the problems that have delta x as a setup, which is what we did 2 problems already, and those that must use dy. Another one of dy's right here. Yes?
Is graphing it the only way you can determine whether he's
Yep.
correct?
Yes, and that was to be my punchline, but you took it, and that's great. Graphing is the only way for you to determine not just what's on top, what's on bottom, what's left, what's right, but also which formula is to be used. So we have all of these problems, 9 through 14, where they just give you functions, and they say good luck. Right? That says, look, regions between 2 curves. Sketch the region and find its area. Good luck. So you graph them on the same coordinate system, right? And then you decide what's on top, what's on the bottom, or what's left, what's right, depending whether it's dy dx or dx dy. So let's pick one of these terrible problems here and solve it. Which one? 11 has a solution in the book. 11 has a solution in the textbook in the back. You sure you want that? Well, actually it has ease, so maybe you want. You want to do ease?
14.
Last one's a little bit the hardest.
Usually.
Usually is. 14, everyone.
I'm good.
14. So by majority of 3 votes in a classroom, we're going to do 14. One person said it, and 2 people nod their heads on it. That was it. 14 chosen. That's how democracy works. You just don't go to elections, and stuff will be chosen for you. Don't worry about it. Yes. The democracy. Y equal 24 square root of x, and y equal 3x squared. They don't give you the limits because they know that you'll be so awesome to graph this, and then when you graph it, there will be intersections, and then you know to set them together, so they don't have to go into too much detail. Great. Time to graph. Exactly. 3x squared is the one that's going to look like this. And 24x is going to look like that. I'm going to intersect there. And we're going to color the piece. Y, x, 24 square root x, and 3x squared. So you already know which one is on top. Well, actually first, do we use left, right, or top and bottom? Ah, we can use either one. Let's do both. Let's go boss mode and do both. So delta x, we use delta x most of the time because we are used to it, right? Used to it. And we don't have to massage these problems in any way, but we'll see that the other one is possible as well. So let's go with the dx first. Integral between two numbers we have to figure out. Which one is on top? 24 square root of x minus the 3x squared, all in parentheses, dx. Now we still need to figure out the intersection. Well, clearly the bottom one is 0. Should I use the word clearly? All right. And then we just need to figure out what is the other intersection point. So we still have to do 24 square root of x is equal to 3x squared. Since you already eliminated 0, you can technically divide. You can divide by root x. You're not supposed to do that. But since you already eliminated 0 as a solution, you know it's a solution. We divide by root x on both sides. And we can also divide by 3. So 8 is equal to x to the 3 halves. Because 2 minus a half is 3 halves. So now we have x to the 3 halves is equal to 8. And how do we solve this problem? Line is going to be too complicated. Yes? Why 6? X. Or instead of 8? What do you want to put there? Why 6? Holding on. What's the opposite of the exponent 3 halves? 2/3 on both sides. Let's not ruin the moment. All right, so x equals cube root of 8 is 2, 2 squared is 4. Still looking at it, right? 2/3. 2 is the exponent, that's squaring. And thirds, it's a cube root. So cube root of 8 is 2. Do that first. And then 2 squared is 4. On the left side, they cancel out because exponent of the exponent, they multiply. So we have x equals to 4. And we just do it now. 24 square root of x, integral of that is x to the 3 halves divided by 3 halves minus x cubed cancels, so just x cubed from 0 to 4. So 3 and 24 will cancel to 8 times 2 is 16 times 4 to the 3 halves minus 4 to to the 4 cubed. And you have 16 times, this is square root of 4. Square root of 4 is 2. 2 cubed is 8, so 16 times 8 minus 4 cubed. Are you ready for the strats in calculating? We're not gonna go 8 times 16. That's too much work. 16 is 4 times 4, right? So 16 is 4 times 4 times 4 times 2. 16 is 4 times 4. 8 is 4 times 2. Minus 4 times 4 times 4 times 1. What's the difference between the two? See that? Well, here it is. Factor out 4 cubed. 2 minus 1, so just 4 cubed is the answer. Or you can do the calculator thing. Yes. Yeah, I know. You can. I mean, you have cell phones, right? And you know that when you flip it sideways, you get more features. Like even Apple has it. So. Then the next comment that I have, which I am ready for so much, but it's live. Oh yeah, thank you. No, because it actually stops the stream. So I just have to go with a comment. Of course, that for Apple users you have to have it. The comments are getting progressively worse throughout the semester until it culminates at the end, like being absolutely terrible. So let's try to kind of keep it civil for at least first month. All right. Well, this was another one, but hey, didn't we say way 2 for the same problem? No line? Maybe this one? Let's do dy because we can. So what are we going to do now? Guys, we have the same exact situation, but we want to use this is 3x squared, and this is 24 square root of x. But we want to use now dy. Now dy formula is c to d, which means it's on the y-axis. Again, c is going to be 0. And it's going to be f of y, which is to the right, minus g of y, which is to the left, everything dy. Please observe that for dy, functions are in terms of y. The functions that are given to you on the graph are both in terms of x. This means that we have to massage these two functions to get x equals function of y. So, the function y equals 3x squared needs to change into x equals the rest, which means you have y over 3 equals x squared, from where x is equal to plus minus square root of y over 3, but then we are going to ignore the negative because it's happening on the positive side of x and y. So we can ignore the negative. The other function was y equals 24 square root of x, which is y over 24 equals square root of x, and then we square both sides to get rid of the square root, so x is equal to y over 24, everything squared. So you see that the functions are a little bit crazier, but we can still do this. because the area is integral 0 to d, right minus left, which means square root of y over 3 minus y over 24 squared, everything dy. To find d, since we know that x is 4, we can quickly find d just by cheating. So d is, I don't know, 3 times 4 squared. You can use the 24 root x, doesn't matter. So 48. So we have a square root of y over 3 minus y squared over 24 squared. Actually, I'm going to put this root 3 and like this. And we don't have to rationalize. So now, as we compute this, it hopefully works out. So what is the integral? We have 1 over root 3. We copy that. Integral of square root of y is going to be y to the 3 halves divided by 3 halves minus 1 over 24 squared times y cubed over 3 from 0 to 48. Are you worried about root 3? Right? For a second I was worried about root 3. But then I spotted that there is a square root right there. So I'm hopeful it's going to cancel. So I have 2 over 3 root 3. And then I have 48 to the 3 halves minus 1 over 3 times 24 squared on the 48 cubed, and then minus big fat 0 for both terms. I'm not even going to bother, worrying about those. That's when I plug in 0 for both terms. When I'm computing that definite integral, I plug in 48 into both terms, and those are these two. And then I plug in 0 into both terms. But in this case, it all cancels because it's all polynomial terms. Ready for strats for computing again? We're going to use the handy calculators. So let's see. Do we all remember that 48 is 16 times 3? Hopefully we do, because that's going to be handy. We get 16 times 3, and it's going to be square root and still cubed, minus 1 over 3 times 24 squared. Ooh, 24 squared. I got 48 over here cubed. I can break that apart as 2 cubed times 24 cubed, and then I'm going to steal 2 of these to cancel. Awesome. So, what do I have over here? I have 2, 3 root 3. 16 is 8 times 2, so that's, oh no, that's cubed. 16, that's 4 cubed times square root of 3 cubed. Awesome. Minus 3 times 24 squared times 8 times 24 squared times 24. And these 24 squares will cancel. Over here I have 3 root 3, 3 root 3 root 3's. So 2 of them will give me a 3. Awesome. So this entire term here cancels with that. Because this is root 3 times root 3 times root 3. Root 3 times root 3 is 3, and then root 3 left over, which is exactly what we needed. And look what I got. 2 times 4 cubed. And on the other side, I have a 24 and 3 cancel, leaving 8 behind. And that's 8 times 8 is 64. Yep. Ta-da. Awesome. What happened? You're gonna meditate on this when you get home. It's like, what the hell happened with the calculation over there? It's like-
I figured out where that 1/8 came from, but I realized it's because we figured about the 24 splits.
Yeah. There is a lot of. You'll grow to love it eventually. Like right now, it's just annoying because you know you have that calculator, right? You know it. And I'm just ignoring the fact. You know that exam calculators are okay, but not graphing ones. That's why you have to pay attention on graphing. No graphing calculators on the exam, and you see the graphing is crucial, so please make sure. We do one more example?
My simple thing is that when we are drawing these graphs, we're sketching them broadly, so to speak. They don't have to be exact.
No. It's sketching. And also, guys, I'm not too much concerned about the calculations and things. I'm much more concerned with you being able to set up the problem, which includes graphing, which includes figuring out the points of intersection, which includes setting up the integral the right way, and integrating, which is calculus. Now, whether you're going to know how to compute the arithmetic on that part, right? So you should know, right? But we are way past that point in our society when that becomes embarrassing, right? Not being able to compute, because now we have the tip calculators. Do we? Do we? Yeah, we do. Should we do a survey?
I know, we don't have to.
Let's not do the survey. Okay. Rachel, how are you? Look concerned for a second. You look concerned for a second. This is good enough. Let's talk about 6.3.